All right, so a big part of Lewis structures and a big part of this course is going to be recognizing formal charge. And formal charge is you can think of it as the charge on an atom. It's not exactly the charge on an atom. It's just the amount of electrons it has relative to its neutral state. And so formal charge, we have an equation here. So formal charge is equal to the amount of valence electrons on the neutral atom minus the number of bonds it has to it, minus the number of lone electrons, right? So let's take a look at an example with methoxide. So in methoxide, we have a carbon with 3 hydrogens connected to an oxygen that has 6 valence electrons. So let's calculate the formal charges on everything. So hydrogen normally has 1 valence electron. Here it's got 1 bond and then 0 lone electrons for a formal charge of 0. Let's check out this center carbon. Carbon normally has 4 valence electrons. Here it's got 4 bonds and no lone pairs for a formal charge of 0 as well. And then finally, this oxygen here. Oxygen normally has 6 valence electrons. Here it's got 1 bond and then 6 lone electrons. Not lone pairs, but lone electrons. So 6 minus 1 minus 6 is -1. So it has a formal charge of -1, and so we need to indicate that. We indicate that by putting a negative sign on it and oftentimes circling it as well. The circling it is not that required, but we do have to put a negative charge on it. Maybe back in Chem 101, you saw something like this, where instead of putting the negative charge on the oxygen, we put it in brackets and then just put the negative charge on the outside. This is no longer acceptable. For our purposes, we need to localize the charge, right? So you must localize charge. That formal charge is not all over the molecule. It's specifically on that oxygen. And of course, in chemistry, things need to be charge balanced. So if you have a methoxide, you have a negative charge, you probably have some kind of positive charge elsewhere. So maybe you have a sodium floating around, right? So the methoxide itself is made out of covalent bonds, but then it's got an ionic bond between this negatively charged oxygen and this positively charged sodium. So you need to get good at formal charge. Let's take a look at some of the most common elements and motifs that we'll see in organic chemistry. So we'll call this OChem, most common elements and motifs. Right, so what are the most common elements we're gonna observe in organic chemistry? Right, hydrogen will be very common. Carbon will, of course, be very common. Carbon is going to be the star of the show. Really, it's in everything. Other common elements include nitrogen, oxygen, and then halogens. So your halogens are fluorine, chlorine, bromine, and iodine, right? So let's think about some of the rules here that we have to follow. Hydrogen will never have more than 2 electrons. Right? It will never have more than 2 electrons. Carbon, nitrogen, oxygen, and fluorine are all period 2 elements, and so they will never have greater than 8 valence electrons. If you draw a compound that has more than 8 valence electrons, a carbon, nitrogen, oxygen, or fluorine, you messed up and you did something wrong, right? They will never be able to break the octet rule. Chlorine, bromine, and iodine, they are capable of breaking the octet rule, but this will rarely happen. So they will rarely have greater than 8 valence electrons. So let's see some common motifs for these elements and check them out. So carbon, the most common way you're going to see carbon is just a neutral carbon with 4 bonds, right? It's bonded to 4 things. And so that's what it does, right? Neutral, 4 bonds, right? They don't have to be all single bonds. They could be, 1 single and then 1 triple bond, right? That's still 4 bonds. But this is the kind of most common motif you'll see in terms of carbon with 4 bonds. But there are other ways we can have carbon. Another way is for it to be positive and then only have 3 bonds. And so if you think about carbon having a positive formal charge and 3 bonds, it has no lone pairs. So while carbon cannot have more than 8 valence electrons, it can have less than 8 valence electrons. And so this is called a carbocation. And will also be pretty common. We'll see that a good bit. The other way you could have carbon is to have a negative charge with 3 bonds and 1 lone pair. So carbon, 1, 2, 3 bonds, 1 lone pair. And then if you think about the formal charge, it has a negative formal charge. And so this is called a carb anion, right? Carb anion. Cation, anion, anion is negative. Cation is positive. There you go, right? So those are the 3 most common forms of carbon we will see in this course. What about hydrogen? So hydrogen, some common forms we'll see is just hydrogen with 1 bond, and then it'll be neutral, right? So maybe it's bonded to a carbon, to an oxygen, to whatever, right? Other ways it could be is an H+. An H+, in this case, it's positive, obviously, and it has no bonds and no lone pairs, right? And so this is just a proton. Just a proton. So we'll talk about things being protonated or deprotonated or a proton transfer occurring. What we're talking about is just an H+ moving around. Remember, hydrogen is just a proton and an electron. So if we take off that electron, we're left with just a proton. And then finally, there's one more form of hydrogen. It's when it's negative and it has 1 lone pair. Right, so we have hydrogen, 1 lone pair, and then it has a negative charge. This is called a hydride. It's going to be less common than our proton and our neutral hydrogen. Next up, we have nitrogen. Nitrogen in its neutral form has 3 bonds and 1 lone pair. So something like that. It can also be positive. In this case, when it's positive, it's going to have 4 bonds and no lone pairs. Right, so positive formal charge, 4 bonds. Think about like ammonium. And then finally, it can be negative. It has 2 bonds and then 2 lone pairs. This is relatively rare, so we won't see it as often, but it will be present here and there, right? But this neutral and this positive form, we'll see quite a bit of those two. Next up, we have oxygen. Oxygen in its neutral form has 2 bonds and 2 lone pairs. And again, there doesn't have to be 2 single bonds. It could be a double bond, something like that. And then it can also be positive or negative, right? So when it's positive, it's going to have 3 bonds and 1 lone pair. Right, if you think about the formal charge there, it's positive. And then it can also be negative, right? Where in this case, it has 1 bond and 3 lone pairs. Right, negative charge. All 3 of these forms of oxygen will be quite common. So oxygen can be neutral, positive, or negative quite easily. And then finally, we have the halogens. So what we'll see a lot, we'll see an X. An X generally symbolizes one of the halogens. Usually not fluorine, but it can be fluorine, right? So X is generally halogen, so I'll just draw X here. So there'll be 2 main forms for the halogens. One will be its neutral state. So when it's neutral, it has 1 bond and then 3 lone pairs. And then 1 when it's by itself. So no bonds and a filled octet, 4 lone pairs. And in this case, if you think about the formal charge, it's going to be negative. So just something to help you out when you're looking at your Lewis structure. These are your most common elements we'll find in organic chemistry, and this is their most common forms that we'll find them in.